So the second speaker this afternoon is Godolphin from the University of Surrey. Janet. I'm so sorry. Janet Godolphin, who will talk about the selection of crossover designs in restricted circumstances. My slip is appropriate after a talk on Alzheimer's. There we go.
Okay, so I guess to be consistent with everyone else, I should start by saying, thank you to the organisers for inviting me. And the work that I'm presenting today is joint work completed by myself, my husband Ed Godolphin, and Simon Bate, who was at GSK when we did the work. So I'll just give an introduction looking at the things at the side there. What I'm going to do today is consider the problem of crossover designs where there's a restriction in the number of subjects that you've got. And the restriction is such that a lot of the work done on optimal crossover designs isn't going to be useful to you. I want to illustrate the problem by means of an experiment into a problem that many diabetic sufferers have, and look first of all for a suitable design in a class of cyclic crossover designs, and then move on right at the end of the talk and look at some non-cyclic crossover designs and see how they compare. So I think probably the first couple of slides aren't really necessary at this stage, but I guess I didn't know where I was talking when I prepared them. Crossover designs. What we're going to be doing is applying T different treatments in succession to each of N subjects. So all my subjects are going to be subjected to each of the treatments. So I'm going to have T periods. So in the first period, everyone gets a treatment. In the next period, everyone gets a treatment, and so on. So T treatments, T periods. What's the good thing about crossover designs? Two good things. First of all, because I'm blocking by subjects, then treatment comparisons that I make are going to be good, because any variation between the subjects isn't going to affect those comparisons. And the second good thing is that even if subjects are scarce, and I am going to be considering the situation where subjects are scarce, then I'm still going to end up with quite a few observations, because if I've got N subjects, I'm going to have NT observations, which hopefully will be large enough to be useful. Now, because each subject is getting more than one treatment, even though in most cases we would hope to be able to allow a nice washout time, we should still allow for first order carryover treatment effects. So all I mean by that is that when you apply a treatment to a subject, there will be a direct treatment effect in the period of application, and you have to expect that there might be a residual treatment effect in the following period. In some studies you can allow for second order and even larger order carryover effects. I'm not going to do that. I'm just going to be considering direct treatment effects and first order carryover effects. This is the model that I'm using. I'm assuming that all my effects are fixed. So mu is the overall mean. Tau and gamma are my vectors of direct treatment effects and first order carryover treatment effects. Alpha are my period parameters, and in the designs that I put up, I'm going to have rows as periods, and beta is my vector of subject effects, and similarly I'm going to have columns as subjects in the designs that I put up. Epsilon is a random vector. I'm assuming that all the elements of epsilon have mean 0 and that they're all uncorrelated with the same variance. That might be unrealistic, but that's what I will assume for the time being. Now, when a design is planned or adopted, we assume that we'll end up with all the observations in the design as it stands. But in practice, there are many situations where observations are not reliable, or they're lost, or they're missing, and they can't be replaced. Type of things that can happen to cause observation loss, at the most elementary level, mistakes can be made. The wrong treatment can be applied, somebody can forget to give a treatment, it can be incorrectly recorded, all sorts of problems. If we have a clinical trial, we can have a situation where for some reason people don't turn up, or they turn up and they're not well enough to be given the treatment, that type of problem. Another cause for observation loss is experimental units can spoil or perish. So I guess here I'm hopefully thinking of something like a horticultural trial rather than a clinical trial. And the last one I've got here is blocks can be removed. So you can lose a whole block, something can go, it can be spoilt, or it might be that the person funding the study basically says, no, I'm sorry, but we've run out of money. You can't do the last period of the experiment. So if we lose data in any way really, then that has unwelcome implications on the efficiency of the design. But in my opinion, the most serious implication can be that the design you end up with, and here I'm using the term eventual design, it can be disconnected. So I'm going to use the two terms plan design for the design that you want to use, the design that you choose, and eventual design for the design that you end up with after you've lost some observations. Right, what does it mean if the design is disconnected? Well, by disconnected here, I mean treatment disconnected. So either disconnected with respect to the direct treatment effects or disconnected with respect to the first order carryover effects. If the design is treatment disconnected due to observation loss, then there are two linked problems. First of all, you're not going to be able to work out your sums of squares to test at least one of the hypotheses that the direct treatment effects are all equal, or that the first order carryover treatment effects are equal. And the second related thing is going to be that many pairwise direct or carryover treatment comparisons are not going to be estimable. You're not going to be able to find a linear combination of the observations which has expectation, for example, TOR1 minus TOR2. And that's obviously very serious. You might be unlucky enough that you can't make comparisons between any pair of direct treatment effects. So a design becoming treatment disconnected is a very, very serious occurrence. Right, so as I said earlier, the situation I'm going to look at is where I'm restricted in my design choice because my subjects are scarce. Why might subjects be scarce? It might be that they're very expensive, like aircraft. It might be that my subjects are people who have a special type of training. They might be animals of a rare genetic strain. Or it might be that due to ethical reasons, we want to use a smaller number of subjects as possible. And I'm probably thinking of animal testing here. Now, if I didn't have that sort of constraint, if I was just looking at if I had no restriction on the number of subjects, but I had P was T, then I can get a balanced uniform design which is universally optimal as long as my number of subjects doesn't exceed T multiplied by T plus 1 over 2, according to Hediat and Yang 2004. So that means that I can choose, there are many designs I can choose where my number of subjects is just a multiple of the number of treatments, and that's great. I can have a nice universally optimal design. But if subjects are scarce, then I might well be in the unwelcome situation where I've got to choose a design where my number of subjects is smaller than my number of treatments. And then all the stuff that's available in the literature, it isn't going to apply, and I'm not going to get a nice universally optimal design. So if I'm insisting that I want a design where my number of subjects is smaller than my number of treatments, I'm probably going to have to search for one using some sort of computational procedure. Furthermore, if I had the option of a uniform design, I would have at least T subjects. If my subjects are scarcer than that, then I have a smaller design, and as such, my design will be more vulnerable to observation loss. So there's a higher risk, or a heightened risk, that through observation loss, my design will become disconnected. And that's something that I want to think about in the planning stage of the experiment. So I'm going to have two criteria when I look for the design that I'm going to use. First of all, not very surprising, I want my design to be efficient. So I want the average efficiency factors for the pairwise direct treatment effects and the pairwise first order treatment carryover effects to be as high as possible. And I guess if I have to make a choice, I'll give priority to the pairwise direct treatment effects. The other criterion that I'm going to use is I want the design to be connected even if I lose a few observations. So I'd like to be able to lose as many observations as possible and still have a connected design. And I guess one question is, are these two requirements compatible? Can I forget about the second requirement? Can I just look for a design that's as efficient as possible, and does it automatically follow that that will have really good properties with regards to being robust against becoming disconnected? So I'm going to illustrate these ideas by means of an experiment into a problem that affects 20 to 50% of the diabetic population, which is diabetic gastroparesis. And the experiment I'm looking at involves 7 treatments to aid this problem, and I'm going to carry out I'm going to plan a 7-period carryover experiment. So my periods are each going to be 1 week long, and each subject is going to be given 1 treatment each week. Now my subjects are going to be 4 specialist canine subjects, and the reason for choosing dogs here rather than something like rodents is because the mechanism that dogs have for feeding is meant to be similar for the mechanism that humans have for feeding. Dogs have discrete feeding periods like humans rather than rodents which browse. And the way dogs chew their food is meant to be similar to the way that we eat, the mechanism, and the way that the food sits in the dog's stomach, again, is similar to our feeding process. So dogs make good subjects in this case. So the treatments are going to be applied orally in the dog's food, and applications are in sequence, and there's a rest period of 1 week between test days, but even so, it's thought that allowing for first order carryover effects is a good idea. And then measurements are taken of gastric emptying. Now, and there are some references. Now, in experiments like this, you can expect spoiled responses. The dogs don't really have the option of not turning up to the period of study, but it's a bit hard to force them to eat or to force them to eat at the right time. So they might not want the food when it's put there. They might eat it a little bit later, and mess up your experiment. Now I'm going to start, I'm aware of the time, but I'm going to start by looking at 2 designs which I'm not suggesting are good. What I've done here is taken the 7x7 Williams Latin square, which obviously isn't balanced. Each treatment carries over to every other treatment either twice or 0 times, and I've designed one consists of 4 columns of the Williams square, and design 2 consists of another set of 4 columns. And I want to show you the problem that we can have if a design becomes disconnected. So I'm not proposing these are fantastic designs. If we look at the second design, then in fact if you lose any 2 observations in the first period, then your design is disconnected. And I've just put 2 asterisks there to indicate a possible set of 2 observations that when you lose them, your design is disconnected. So those 2 observations are spoiled. Now, what does that mean? Why is that disconnected, and what's the consequence in the case for that design of it being disconnected? Well, any linear combination of treatment effects, and there I've written it as lambda dash Tor gamma. Remember, Tor is a vector of direct treatment effects and gamma is a vector of first order carryover treatment effects. Any linear combination like that is going to be estimable as long as lambda is orthogonal to all vectors in the kernel of the information matrix. So in this case, my information matrix is going to be a 16 by 16 matrix because I've got 8 direct effects and 8 first order carryover effects. My original plan design too was connected. That's fine, I wouldn't start with a disconnected design, and it had 2 vectors in the basis of the kernel, and there they are, V1 and V2. So the first 8 elements refer to the direct treatment effects, and the last 8 elements refer to the first order carryover effects. So you can see that if you want to estimate, say, Tor 0 minus Tor 1, then that's fine, because the vector, my lambda vector would be 1 minus 1 and then 14 zeros, and that's going to be orthogonal to V1 and it's going to be orthogonal to V2, therefore it's estimable and fine. Any contrast in the direct treatment effects and any contrast in the first order carryover effects is going to be estimable. But once I've lost those 2 observations, then that induces an extra relationship between the columns of the design matrix, and I've got an extra basis vector in the kernel of my information matrix, and it just happens to be that one, not a very nice looking vector. But now imagine you want to estimate Tor 0 minus Tor 1. So remember what the lambda vector looks like. It's got a 1 and a minus 1 in the first 2 positions and everything else is 0. And now look, what's the problem is that it's not orthogonal to V3, so it isn't estimable. In fact, you can see that any direct treatment effect, any contrast involving direct treatment effects is only going to be estimable if you've got the same element here. So Tor 1 minus Tor 2 will be estimable, Tor 3 minus Tor 4 will be estimable, nothing else. And similarly for the first order carryover effects. So the only estimable ones are those. There are a lot of other estimable contrasts involving more than 2, but do you want to know that Tor 0 plus 3 Tor 2 minus Tor, something is estimable? Perhaps not. So, in fact, there are 15 ways that you can lose 2 observations and you get a disconnected design for that particular one. I need to speed up a little bit, don't I? And there are 448 ways in which you can lose 3 observations and it's disconnected. So if you think there's a chance you might lose observations, then you need to perhaps rethink the design. I'm going to move on here. Here's a summary for the 2 designs together. So you can see the first design, which was 4 columns of the Williams square, is considerably better than the second design. Neither of them look amazing. And look at the efficiencies here for the design we were looking at. You might be thinking at the moment, oh, well, we can forget about worrying about the number of observations we lose because this design is so rubbish anyway when you think about efficiency that we wouldn't even consider using it. We wouldn't even worry about how many observations you lose for it to become disconnected. Right. Now, what this is showing us is that designs of very different calibre can be got just by selecting different subsets of the same square. Now, moving quickly on to what I wanted to talk about. Russell in 1991 introduced some small cyclic designs, and we extended these in a paper that's just come out in 2008 in CSDA. The idea for both approaches is that we select 4 columns from a nearly balanced cyclic Latin square, which we call a parent square, and basically look at the properties of those. So what Russell does is he considers the Russell square. So if he has an even number of treatments, he's basically looking at the Williams square. For an odd number, he's got his own square. So with the case for n is 4 and t is 7, he basically has 1 square leading to 5 different designs. All we did was say, rather than look at one nearly balanced square, let's look at all the nearly balanced squares. So we had an algorithm to generate all the nearly balanced squares of order 7, and there were 30 of them, which led to 30 times 5, 150 different designs. These are the best designs. The Russell design on the left-hand side and the BGG, Bake Godolphin, Godolphin design on the right. So all they are 4 columns each of different nearly balanced squares. And here are the properties that they have. So I've put the properties of the BGG design, the Russell design, and one of the designs made up of 4 columns of the Williams square. You can see that the BGG design has come off best, which I guess is why I'm presenting it, but there's a negative bit in a bit. So the efficiencies, they're not bad. They're not too dissimilar though from the Russell efficiencies, but it's considerably better with regards to design loss. You can lose any 3 observations and it's still connected. You can lose 4 observations in 25 ways and it's disconnected. But really, I guess if you only have 28 observations, you would hope not to be in a situation of losing 4. Russell design is not so good with regards to observation loss because you can lose 3 observations and it's disconnected, and there are 54 ways you can lose 4. However, the Russell design is quite a lot more efficient than the design from the Williams Latin square, which came out better with regards to observation loss. So there you can see that it doesn't follow that a design which is more efficient is always better with regards to observation loss. So the Russell design is more efficient, but it's not so good with regards to observation loss. And that's just summarising that there. Now we actually looked at 150 different designs, and here they are ranked. Here are the first 12 ranked in order of efficiency. So I've ranked them in order of the efficiency of the direct treatment effect contrasts. Now, the one that I've coloured in blue is the one that I would choose to use. It isn't the most efficient, but it's not bad. And look at its properties with regards to observation loss. It isn't as vulnerable. You can lose any 3 observations and it's still connected. So I would say that was considerably better than any of the ones which rank higher up, which all become disconnected or can become disconnected by the loss of 3 observations. You'll notice there is actually 2 designs with the same efficiencies. Now of them I've chosen this one simply because it's 4 columns from a terrace, but there's no reason why I couldn't choose the other one. In fact, they all seem to come in pairs. I can't work out why they come in pairs. They are definitely not isomorphic, but they come in pairs with regards to the efficiencies, which I think is quite interesting, but I can't explain. Design 10, which I've coloured in, is the Russell design. So that's quite good as well. Now the negative bit, just say quickly, there were 150 designs. This is the worst one. You can see it really is much worse than the ones that we were looking at, because you only have to lose 2 observations, and you can do that in 2 ways for it to become disconnected, and the efficiencies are considerably worse. So at this point we were feeling quite smug, I guess, but then we looked at the computational search routines of Eccleston and Whittaker and John and Russell, because they produce designs which aren't columns of cyclic Latin squares, which are more general. I'll be very quick now. So and we used the algorithm several times. There's the Eccleston-Whittaker design, the best one we came up with, and the John Russell design. And if we look at their properties, right, you can see that the efficiencies are very, very good. And we came up with one design using the Eccleston-Whittaker approach for which you could lose any 4 observations and it was still connected. So that was really good. Having said that, both routines, the Eccleston-Whittaker and the John Russell, often gave us designs which had repeated treatments for the subjects, and occasionally gave us designs which had non-zero values here So what I'm trying to say in conclusion is that these search procedures do give very good designs, but it's a really good idea to check for the number of observations that you need to lose before the design becomes disconnected. And if you want a cyclic design, and in talking to at least 2 pharmaceutical companies, for some reason they seem to think that cyclic designs are easier for their staff to implement in practice. If you want a cyclic design, then I would recommend the designs, the BGG designs. The BGG approach gives you a method for finding all the nearly balanced squares of a certain size if you have an odd number of treatments, and then we have a routine for finding the set of columns from those squares, which gives you the best design with regards to efficiency and observation loss combined. So I think I've run out of time, haven't I? So I think I'll stop at that point.
Well, thank you. Terraces were mentioned first.
Yes? Well, I know what a terrace is. I don't know.
Don't hear them every day. Angela, yes.
Did you, after, I mean, I've understood exactly what you've done here, so now I'm wondering, okay, these designs are really good for that model. Now, what about other models? Have you looked at how well they perform?
You mean other sizes of?
No, other models like second order carryover or interaction between the direct and carryover effect?
Not completely. The first point, we're looking at some not small designs like this, no. What I have done is looked at sets of squares which are balanced for more than first order carryover effects when you put them together, but that's a slightly different problem, yes. Yeah.
Okay, well, perhaps we should press on. Thank you very much.